So we have been developing equations for different coordinate systems so far. So for example, if we just look at some of our development, some of the problems we've been working on, we looked at, let's hope we have enough of this here. So in the cylindrical coordinates, we got an equation that looks like this. And so in cylindrical coordinates, we had the z direction. So we had ddz of uzca, and then we had ddr. And the ddr part was a little bit different in that we needed to retain an r inside of the derivative. So it's not the same as with z. Z doesn't have a z times this, but with r, you have to have an r times this. So that's what we had in cylindrical coordinates. In rectangular coordinates, right, with this rectangular drug substrate example, we showed eventually that this was the equation that we got. And so we didn't have flow, so this was just diffusion. So we didn't have the flow terms, so we didn't have those terms. We had just diffusion, and this was rectangular coordinates. So we didn't have z times anything. It was just d2ca dz squared. So those we had. Then I'm looking for one with spherical. Yeah, here's one with spherical coordinates. In this case, where we had the components diffusing to the particle and then diffusing out, we derived that even though it was just diffusion, still we had DDR of DDR. So in here, you can see another DDR, and we had an R squared there. So it looks like when you use different coordinate systems, it's not just that your choice of variables change, but sometimes you have these little artifacts like an R for cylindrical, now an R squared for spherical. And for rectangular, there's no z squared or anything. And one of the things we would like to do is tie all this into one general framework and say, here's the equation that describes mass transfer. But it looks like we can't really do that because we have all these weird little R squareds or R's or no R. But you see, if you go over to so going back here to the conservation equation, what we can do is define an operator. So the del of a function in Cartesian coordinates, it looks like this. So in rectangular coordinates, that's how it's defined. And then the del squared is defined like this. Then for cylindrical coordinates, you can show that you have a 1 over r times df di theta. Well, that term we don't normally have. We just normally have a df dr. But for the second order term, you will find that it's 1 over r ddr rf dr. So this in cylindrical coordinates is what we get for the del squared. And by the way, this is not merely a definition. There are rigorous relationships between these coordinate systems. So for example, if you have RYZ and theta RZ, you can define the relationship between these. So you can say, for instance, X equals R times cos of theta, Y equals R times sine of theta. For Z, there's no difference, Z equals Z. So there does exist a rigorous relationship between these coordinate systems. You can transform between one variable and all the other variables there. So that's what you can do in cylindrical coordinates. For spherical coordinates, we have r theta 1, theta 2. And the relationship between x and r and theta 1, theta 2, I think it's x equals r cos of theta 1 times sine of theta 2, and so on. So you can define the relationships. You just have to draw out the geometry. So just to show how you get that, if you define your axes to begin with, so let's say that's x and y, and let's say z is coming out of the page like this. So you can define to begin with your your rectangular coordinates, and then you can imagine spherical coordinates. So you can imagine a sphere sitting around this space. So let's draw a sphere here. So if you have spherical coordinates and then you pick a point somewhere on that sphere. So if you pick a point here, for example, then you can project that point down onto the plane in, I guess this is the XZ plane. And then you can project here and project. So you can project onto the XYZ lines. Sorry, onto the XYZ, onto the axes. So this point, at this point, we can, this point which is somewhere on the surface of that sphere, and maybe to emphasize that, we can draw a little ring here. This is at a certain radial position. So let's see, this will get a little harder now. So here we have, we are pointing out of the page, and that's also, we can also draw a line like that to meet there, because then we can say there's an angle here, and there's an angle here, and this is R. So we've got R, θ1, θ2, and we can also write X, Y, and Z. And we can relate all of these to the point using X equals R cos θ1 times sine θ2 and so on. So we can definitely find relationships among these. And then you can, if you differentiate, for example, if X is written in terms of theta, then if we want di f di theta, then we could write di f di x di theta. And so if you do all that, then you get these nice relationships that tell you how your del and del squared operators look in these different coordinate systems. And so the point of doing all this is not to make pretty equations, although that I won't say that's not part of the motivation, but the real power of doing this is that now you can fully generalize your equation expressions, which means that instead of saying that, oh, all my equations are dependent on my geometry, right? Instead of saying, okay, in cylindrical coordinates, the equations look like this. In spherical coordinates, the equations look like that. So instead of having to do that now, we can write one equation like this that applies to every possible situation. So this equation, written in terms of these del operators, written in terms of the divergence, this is now applicable in any coordinate system. So whether it's rectangular, spherical, cylindrical, or you could define any weird, or well, not weird, but you can define any coordinate system that you want. And as long as you define, or if you work out the relationship between that coordinate system, or you can then define these operators for that other coordinate system. So this equation is general, it applies always, and it's got all the concepts that we want. So we have convection going on, we have diffusion going on, and this is more for if you have, for example, reaction or something like that. We didn't really deal with this, so just ignore this G part now. So this applies, and if you go back and look at all our examples, and I'll leave that to you for an exercise. If you go back and look at your concrete slab, or your cylindrical pipeline, or your diffusion away from the spherical particle, if you go back and apply the operators for this, you'll see that we always got an equation that was consistent with this. So the tremendous step forward for us now is that we have totally generalized our situation with respect to geometry. It doesn't matter to us anymore what the shape of things are. So that's the great advantage of defining these operators. Now, that's one level of generalization. The other generalization that we can consider is that there are, of course, other balances that we could be writing. So, for example, there's the energy balance, right? And in terms of counting energy, if you think of a fluid in flow, then as the fluid is moving along, so that's convection. And so if you think of Cp delta T, your fluid convecting is going to have a form like this. And then through the fluid, you also get conduction of heat. So conduction also contributes a form like this. So in terms of the energy balance, you also start to see a kind of equivalence. So in the same way that in terms of mass, we had convection and diffusion terms, in terms of energy, we also have a convection term, and we also have a diffusion term. And fine, we don't actually call it diffusion in terms of energy. We call it conduction. So think about a metal rod. If you heat one point on the rod, you can imagine that the heat will flow towards the colder part of that rod. And so the whole rod will heat up slowly. So that's, if you like, diffusion in the energy sense, in the thermal energy sense. So the same things that we've been talking about can be applied in the sense of temperature and energy. And then equivalently, if we think about a momentum balance, you'll find that your momentum balance also has the same form, that there's the convection of momentum. So momentum is simply carried around. The fluid, just because the fluid itself is moving, then it will carry its own momentum as it's moving, right? Well, I guess that's a kind of circular argument, right? Momentum carries itself because it's moving. But anyway, that's convection of momentum. And then we also have that the fluid does drag itself. So viscosity tells us how tightly the fluid drags itself, right? So you can think of viscosity, right? We think of it as like the stickiness of a fluid, right? If you plunge your hand into a jar of water, you'll have a different experience to if you plunge your hand into a jar of honey. So your viscosity is higher in the case of honey. That's because there are more electrostatic attractions, or the electrostatic attraction is stronger between the honey molecules and the water molecules. So they move apart more slowly. They are more tightly bound together. So viscosity or viscous drag is another concept. And if you imagine honey in flow in a pipeline, then if in the center of that pipeline, you've got fluid flowing faster than the rest, you can imagine it's going to drag the neighbors around. So it drags on the neighbors. So that's like diffusion of momentum as well. Your momentum is tending to convect in one direction, but then that momentum, that force, is also dissipated radially as it's contributed to its neighbors. So diffusion of force, this is diffusion of energy, diffusion of mass. And if you do the derivation, you'll find it has a second order dependence with velocity, energy second order with temperature, mass second order with the mole fraction or concentration. And so in a way, all these balances have the same form. So those are two huge generalizations that we are looking at here. One, a massive generalization in coordinate systems, in spatial dimensions, and two, a generalization in terms of the nature of the balance. By the way, I noticed also in electrical engineering, you have current flow and your voltage gradients. It's the same concept. So it's not the case that it's just the three we know in chemical engineering. So if you look at the Poisson's equation in electrostatics, you also get this kind of relationship. So those are the generalizations that we want to start looking at. And this introduces the topic of analogies among mass, energy, and momentum. Now, with the next section of the course, and that's, of course, Mr. Biela will be seeing you for that. He will be taking you through the details of energy and momentum balancing. But we are just at this stage going to introduce these concepts and start thinking about the analogies that arise in these areas. So already we can see the equations look similar to each other. So are there some other relationships among these equations that we can exploit and that we can use to simplify the developments that that we want to create? Okay, any questions or comments on any of that? Okay, if not, I guess we've reached the end of the session for today. Then the next session is on, well, I think tomorrow is a real Tuesday. So today we followed Tuesday's timetable. My understanding is tomorrow's timetable will also follow Tuesday. So I guess I'll see you at the same time tomorrow.
Sorry, sir. Yeah, I wanted to ask especially about the test. Is it going to cover everything up until the energy balance equations, up until the conservation equations?
Yeah, so someone did ask the question earlier. So I'll be sending out, a detailed note about the test, and then we'll cover some of the material more during the revision sessions as well. So I'll send out a note about the test material.
Okay, perfect. Thanks.
Okay, then if there are no further questions or comments, I guess that's it for today.